Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation on section 2.4, the chain rule. I know some of you guys have giggled about my intro, and so I thought I'd share where I got that from. It's an old 80s sketch from SCTV. So that's where I get it from. You can have a good laugh. Let's get to it though. Today we're talking about the chain rule. The chain rule is a fairly important section of calculus. It is something that we will be using over and over and over again, and it is certainly a concept that you will need to be fairly well versed in as we move into the last two sections of this chapter and as we move into integrals, because we will be using the chain rule as a method of solving integrals later on. And so we're going to talk about a specific instance of the chain rule, and that is the general power rule. And then we're going to simplify some derivatives. And then we're going to also talk about the trigonometric functions using the chain rule, specifically sine and cosine. Okay, so what is the chain rule? There is a calculus help video, and they have some nice animations that I don't have the power to do, so I thought I'd give you a quick break here to go check that out. So pause and go to that. It's also in my description of this video. So here we go. Pausing in 3, 2, 1, moving on. Okay, so here's the chain rule. The chain rule is a way to find the derivative of the composition of two functions. And I've got plenty of examples that I'm going to do here, but just in general, if you have two functions, an outer function composed with an inner function, then the derivative of that particular function is going to be, you're going to do the derivative of the outer function, leaving what's inside alone, and then multiplying that result by the derivative of the inner function. Now, when you see something like this, we're taking the derivative of some function u, and so whenever you see d over dx of some function u equaling to d will be du over dx. This u is, let's see here, a function in terms, F-U-N-C-T-I-O-N, in terms of x. So this is just some way of abbreviating another function. All right, so the general power rule is an application of the chain rule. So if you have some function raised to a power, then the derivative of that is you're just using that simple power rule that we used, and then only with, instead of it just being x to a power, it's a function to a power. We bring the exponent down front, reduce the exponent by 1, and then because it's the chain rule, we have to multiply by the derivative of what's inside. Again, u, some function of x, to the end, take the derivative of this expression, we bring the exponent down, reduce it by 1 and leave it there, and then multiply by the inside. So a real quick example. If I were to say f of x is equal to, let's say, x squared plus x to the fourth. Now, I have a function, this function in here, this x squared plus x function, is the inner composed function of the x to the fourth function. So the derivative of this thing is just going to bring this 4 down, so it'll give me a 4, and then it'll be x squared plus x. You leave the inside alone, and then reduce it by 1, and then multiply by the derivative of the innermost function, which would be 2x plus 1 as that expression. Now this is good enough for right now. I don't think it's reasonable for me to ask you to multiply all of these out, especially if it's x to the third, and then multiply by that x squared, or 2x plus 1, and then multiply by 4 again. That's a little bit more work than what we really need to do here. All right, another example. Find the first derivative of the function. This is from page 137, number 12. And so we're going to do a lot of rewriting here, and I'm going to talk about the functions just in general. So I am telling you right now that f of x is equal to the function h of x composed with g of x. Now, just take a real quick pause here and try and determine on your own what h of x is and what g of x is. So just pause, give you a second. 3, 2, 1. Okay, h of x and g of x. What do you think they are? That's what you should be thinking right now. And the correct answer for this is h of x is square root of x. That's going to be my outermost function. And I'm going to rewrite it as x to the 1/2 power using my rational exponent rules properties. And then my innermost function is going to be this 9 minus 4x. All right, so I remember from my chain rule that f prime of x is going to be the derivative of the outermost function, leaving the inside function alone, and then multiplying that thing by the derivative of the inner function. So if I go through and I do these, h prime of x is going to be a half x, and then when I subtract a half from a half, I get negative 1/2. And we're going to simplify this eventually, but for right now, that's okay. And then g prime of x, the derivative of this, is just going to be negative 4. So filling in the blanks here, my derivative of this inner function is going to be a half times, well, g of x left alone is 9 minus 4x, all to the negative. Let's erase that. I got a little, oh, darn it. I hate it when that happens. Let's do this a little, let's redo that. There we go. I get 9 minus 4x to the negative 1/2 times the derivative of the outer function, which is just negative 4. All right, so let's simplify here. I want to get rid of my negative exponent, so I push all that to the bottom. So I got 9 minus 4x. This is all going to be to the 1/2 power. And then I've got a half times negative 4 is negative 2. That stays on the top. Now again, normally we probably wouldn't leave the half in the bottom. I'm not going to worry about that a whole lot. Just realize that on the AP Calculus test, they may multiply. This may not be one of the multiple guess answers. They may multiply or rationalize the denominator by multiplying this by 9 minus 4x to the 1/2 over 9 minus 4x to the 1/2, and doing a little bit of simplification. All right, let's move on. Let's talk about the trig functions. And again, whenever these are chain rule expressions of the derivatives of trig functions. So when you see this sine u, this u is a function of x. So when you see down here in my example, when you look down here in my example, you say sine of 2x to the third. Well, this 2x to the third, this is a function of x. This right here is my u that I'm looking at. So when you say, okay, what's the derivative of that? It's the cosine of u. So we're going to leave that alone times the derivative of whatever that u is. So, and then this expression here is just another way of writing this, where this u prime is rewritten as in differentials, which is du over dx. All right, and you need to be able to do both. There's just no way for me to say that it's okay for you to just understand this one or just understand this one. You got to know that both of these two things mean the same thing. All right, so let's talk about how we're going to do this. Well, this derivative here is going to be, again, we're doing the derivative of the outer function first. So the derivative of sine we know to be cosine. And so we're going to say it is the cosine, leaving the inside function alone, 2x to the third. And then we're going to multiply that thing by the derivative of the outer function, which we know to be 6x squared. Now, I can't do a whole lot of simplifying about this for this function, but just because it's cosine and we don't want to take the cosine of all of these things, just the cosine of that, I am going to rewrite it as 6x squared times the cosine of 3x to the third. Now, we can also have, and this is going to be my final answer, there's not a whole lot else I can do with that. We can have a composition of multiple functions. This is actually the composition of three functions. The outermost function, so my outermost function is going to be y equals x squared. My middle function is going to be y equals cosine x, and my innermost function is y equals 3x. So you can see that composition going on there. And so when I go to do my derivative of this, I've got to do the composition multiple times. So when I take the derivative of the outermost function, it's times the middle function times the derivative of the inner function. So this derivative is going to be, and again, applying the simple power or the general power rule with 2. I bring the 2 down, and then I leave everything on the inside alone, cosine of 3x. Now this is to the first power. So now the derivative of the innermost function, this cosine function, which is a u function, is going to be negative sine, leaving the innermost value alone. So I have my 3x. And then I have to multiply that thing times the derivative of the inside of that, which is just 3, not 6. I don't know why I wrote 3. So it's 3. And so there's, again, not a whole lot of simplification that I can do. I've got this negative, I got a 2 and a 3, so let's make it negative 6 there. I don't need to write my exponent, so cosine of 3x, and then we'll multiply that by the sine of 3x. And I don't think I can simplify that any further. And so that's done. That's not a j, that's parenthesis. Okay. All right. Moving on, some examples. This is evaluate the derivative at the given point. I've picked this one to try and kill 2 birds with 1 stone. The first bird I want to kill is a lot of students who look at this particular problem. The first thing I'm going to say is, uh-oh, I got to do a quotient rule. And you don't, especially if you learn how to rewrite. Because this thing right here is a constant, I can use a version of the constant multiple rule, and I can rewrite this particular expression as f of x equaling to x squared minus 3x all to the y third, come on, Macaulay, x squared minus 3x all to the negative 2 power. And I can do that because it's because of the constant. Now, if it was x on the top, I'd have to do the quotient rule. There's no way around that. But because there's a constant, and even if it was like 4 here, if there were a 4, I could leave the 4 out front if I wanted to, if this was 4. It's not. I mean, I gotta erase that. But if it was, I could just leave that 4 out there. So if there's a constant in the top, rewrite it with a negative exponent, and that'll make you doing your derivative easy. The second thing that I want to talk about, the second reason I did this is because it says evaluate the derivative. And what that means is basically what is the value of the derivative at this point. So it basically tells me to plug in 4 and come up with an answer. Now, when you get to something like that, you know, when we do a lot of these derivatives, you're going to end up having to do some reducing. That being said, if they want you to find the value of a derivative, don't worry about reducing, okay? We want to reduce the amount of work that we have to do. Calculus is a lot of work as it is. So in this particular instance, since they want the value of the derivative, my suggestion to you would be to just find the derivative to a point where it's usable to you and then plug in. So if I'm doing this derivative using the general power rule, I'm going to say that this is, I need a pen to do it. I'm going to say that f prime of x is, I bring that negative 2 down front, I leave the inner function alone, and then I reduce this by 1. And again, don't make the mistake of saying that this is negative 1 now, because it's negative 2 minus 1 is negative 3, times the derivative of what's inside, which would be 2x minus 3. I take the derivative of that expression right there. Now, here's the thing. If I said find the derivative, I would expect you to reduce this in somehow and simplify. If if it's possible. But that's not what they want. They want us to find evaluate the derivative. They just want f prime of 4. So I can use this as is. Why waste the time simplifying if I'm going to plug in anyway? So let's go -2, and then it is 4 squared minus 3 times 4. And this is all going to be to the -3rd power times 2 times 4 minus 3. And so we can evaluate that again. -2, and then this will be, let's see, 4 squared is 16 minus 12 is 4. This will be 4 to the -3rd, and then this will be times 2 times 4 is 8, minus 3 is 5. That'll give me, let's see here, 2. This will be on the top. This will be pushed to the bottom because of the negative exponent. So I have -10 on top, and then 4. 4 times 4 is 16 times 4 is 64. So I got 64 on the bottom, and then that'll reduce down to 5 over 32. And this thing is the value of the derivative at x equals 4. That's what it is. All right. Last example. Again, you can have multiple compositions, and then when you use the chain rule on all of these, you start on the outside and you work your way to the inside. So this function here, I have my outermost function is an x to the 3rd function. Then the middle function is this expression here with an x to the 4th. And then my innermost function is just this x squared plus 1. So when I go to do my derivative of g of x, again, applying the general power rule, I bring the 3 down front and I leave everything on the inside alone. So it's 2 plus x squared plus 1 to the 4th, all now to the 2nd power. That times the derivative of what's inside. Well, the derivative of a constant 2 is 0, and then the derivative of this function, I'm going to need to do, again, a general power rule on this x squared plus 1 to the 4th. I bring my 4 down, I get my x squared plus 1. It's now to the 3rd power. And now I have to multiply this thing times the derivative of the innermost function, x squared plus 1, which is just 2x. Now, simplifying this thing, I am going to have to simplify. I've got a 3, a 4, and a 2x. That's going to be 24x. We'll leave that, so all of that's done. Let's see here. I guess I'm going to go my x squared plus 1 to the 3rd. And then all that's left is this expression here. So it'll be 2 plus x squared plus 1 to the 4th all squared. And I am happy with that solution. I think I have everything, and I multiplied correctly. I think I'm good. So I'm going to leave it as at that. Well, that's all I got for the day, folks. But since I rushed on the first 3 of these videos, I'm getting back to the Star Wars fun facts of the day. This kind of went down on me. But in 1975, when they made the original Star Wars, A New Hope, they didn't have 3D printers and they didn't have all kinds of great special effects. They kind of just had to make up their own stuff. So when they built the prop for Luke Skywalker's lightsaber, they just went around the junk and started tearing stuff apart and started sticking it together. So Luke Skywalker's lightsaber is actually an old-timey flash camera handle where they took off this round part and this little black part here. And you can actually see the little screw is still, there's a little screw right there with, they probably used a different little screw there. And they got these clippy things on it. And so that makes up the major part of that. And then like here, you can see these little LEDs there. They tore apart an old-timey 70s calculator, and they used the light strips there. And then they took a windshield wiper blade and they cut it up into strips and they glued them onto the back. So that's what these little black strips are. They're just windshield wiper blades. And so that is, I just kind of did it. The old-timey flash camera handle, the innards of an old-timey calculator plus a windshield wiper blade gives you Luke Skywalker's lightsaber blade. Well, folks, that's all I got for today. You have a great day, and I will see you in class. Goodbye.